All right. Hello, everyone. Welcome to Lecture 16 on Computing Platforms, a special late night edition of Scalable Software Architectures. Last time we talked about authentication, and this was needed when you were designing a web service that you had clients connecting to from the outside, particularly very often smartphone apps or browser apps that were using where users were logging in, and they were making requests to the backend, and those requests to the backend had to be restricted to they were fetching private information, or they were interacting with a particular user's account. So the user logged in with the username and password, and then for later when they did that, they were given back an authentication token. Whoops. And that token was included in future requests to essentially tell the backend who you were, and so the backend would be able to check that authentication token indeed matched something that was stored in the database, and therefore to decide that it would trust your request, or it would know, and it would know also who the request was coming from. Yeah, but today we're going to be talking about computing platforms, and this is really about three different topics that are interrelated, which are packaging, distribution, and deployment. Okay, so unfortunately, when we're writing code and distributing code, it's hard to make it run anywhere. Usually there's a very specific environment required for your code, because there are a lot of different varieties of computing systems that have been deployed for different needs, different operating systems, different libraries, and whatever. And any one particular app requires usually a specific combination of components to make it work. So for example, you might need a particular application server like Tomcat, which we use in some of the homework, or Node, or Maven, is a tool that you might need to deploy your software. You're usually writing code in a particular language, and you might need that language runtime or interpreter to be installed. For example, a specific version of Python. If you're developing in Python, the version that's installed on the target system needs to be similar to the version you developed for or developed on. Same thing goes with Java. Java requires a runtime environment. If you're deploying your code as source code, you might need certain libraries to be installed for it to compile and run. You might also need certain command line tools to be installed. So, for example, you might need a database process to be present, like MySQL might have to be running on that machine. You might need to have some kind of open source software, like ImageMagick is a image conversion software that runs on the command line, and very often if your software needs to do some kind of image conversion, it'll create a background process to do that essentially on the command line, except programmatically on the command line in a shell, or some kind of encryption primitives might require command line tools. And you might also need the operating system you're running on to have particular features or to be configured in a certain way. Like, for example, you might expect there are certain folders to be present because you're going to be loading files or saving files in there. You might expect certain permissions in certain folders. You might expect the firewall to be configured in a certain way to let network connections in or out. All that's part of the environment, which you can set up manually on your machine or on a given machine. But if we're deploying a scalable system, you want that deployment to be kind of automated and standardized, so that you don't have to manually go in and configure all these machines. You want to be able to to package your software in such a way that it can be delivered and distributed and deployed with as little intervention and in as automated a way as possible, right? So very often when you're writing code, you find that it worked on my machine, like when you're working on homework, but it doesn't end up working on the TA's machine for grading. Right, the same is true in the real world when you write code. It just gets worse because your code gets more complicated, and that means that the requirements for the runtime environment get even more complex than they would in kind of a homework assignment, right? So the problem just gets worse and worse. There are several different solutions. We're going to talk about some of those today. We're not going to talk about everything because this is a complex topic, but we're just going to kind of go over some basics. And these include things like the Java virtual machine, full virtual machines, containers, and serverless functions. And we can classify these as either packaging or distribution or deployment technologies, or a combination, because these are all interrelated. So it gets a little bit confusing. Before we get into this, I want you to kind of stop and think about this to kind of motivate it for yourself. In your experience, writing code, using code from the internet, maybe downloading open source software, you've probably had some experiences trying to run other people's code. Maybe running your partner's code for a homework assignment. And what have been your worst experiences doing that? And what have been your best experiences? In other words, have you found that certain languages or platforms or operating systems make this easy or hard? And what about them make it easy or hard? And also, if you've written code that you wanted other people to use, for example, if you had a really nice solution to a project for, I don't know, let's say your networking class, and you wanted to post that on GitHub or something for other people to use, although if it was my networking class, please don't do that because those are homework solutions other people will use. But anyway, yeah, if you've written code that you want other people to use, have you tried to do that? And if so, like, did you actually hear that anyone else used it? I think you might find that it's actually pretty difficult to do that because you have to document things. You have to either set things up in a way that's reproducible or document every single little step you did to set up your system and make that documentation work for a variety of systems. So stop and think about that if you have some experience, and maybe you can come up with some principles or like examples of what a good software packaging and distribution platform is, and what practices work and don't work. But anyway, you probably have found that some languages or features or tools make the process easier. We're going to talk about some of that stuff today. Okay. So the first option you might think of when talking about distributing apps is to distribute a binary executable. And this is typically done for consumer software on consumer operating systems. So if you buy or download a Windows or Mac application, or if you install an app on an Android or iOS device from an app store, either way, whether you're using an app store or an installer program, what you're doing, you're not downloading source code. Typically, you're downloading a binary executable that was compiled. And it's compiled to work on a specific machine or specific set of machines. And that works well for Windows and Mac and Android and iOS because those platforms are highly standardized. They're designed with this explicit intention of users buying software and installing it and running it, right? So there's a lot of care taken to make these consumer OSs backward compatible. Like, for example, if you're using Windows 10 today, you can still run apps that were compiled for Windows XP in 2001, so like 19 years ago. And if you're 10 years ago, if you're using Windows XP while it was still supported, you could run apps that were compiled for probably Windows 3.1 in 16-bit mode. I think those would still work. So again, you could go back 20, and usually you can go back 20 years, I guess is what I'm saying, with Windows and run 20-year-old software, which is pretty impressive, given how much has changed on the operating system side. And that works because, again, the developers of the operating system have been very careful to make that work, and also they've released a lot of tools and libraries to make that happen. And for the app stores, they have a lot of control over the kind of the build system that you're using. Like, for example, if you're developing an iPhone app, you have to use Apple's Xcode developer tools to compile it and sign it. And that whole process creates a very standardized executable that will run on all the different like iPhone devices that are supported at that time. So that works well for consumer OSs where the OSs are very standardized and where you can force the developers to use certain tools. But it's kind of a rigid system. And actually, if you're a developer of these, if you've ever developed, let's say, an iOS app or a Windows app, you probably felt a little bit constrained by the fact that you had to use these tools and you had to like use the libraries that they provided. It's not a very flexible system to work with. So it doesn't allow for a lot of innovation in like the languages that you're using, that you're able to use, and the libraries that you can use, and all that kind of stuff. So that's generally not what we don't generally use this approach with server software because we want to use more. We want to have more flexibility in the way we write our programs, and we want to be able to run them on in particular, open source operating systems like Linux that don't have this whole like highly structured deployment system. Although you can certainly compile code to run on Linux and distribute binaries, and that'll sometimes work, but there's so many different variations of Linux that typically what you end up doing is distributing using the second option, which is to distribute source code along with some instructions like a README file or a build script like a makefile or the equivalent in different languages to build the code. Now, theoretically, this should allow your code to run on a larger variety of systems. Like, for example, if you write code in ANSI C, that will run, like a C compiler should be able to compile it on like a ton of different systems, almost any kind of machine, including really old machines and new machines. But in practice, there are some little differences, and there are a lot of libraries being used, and if any of them do anything at a low level, then you end up with incompatibilities, and you'll see that when you're compiling, the compilation will fail. So even if you distribute source code, which theoretically is in a language that's supported on your platform, there's a high likelihood that it still will be difficult to reproduce a working environment, and you'll have the same situation where it doesn't work for the person trying to use your code, even though it worked on the developer's code, on the developer's machine. So this is okay, but I guess it's not totally automated because it's very flexible, and it doesn't constrain the deployment environment at all, and that means that it's liable to fail on a lot of those exotic environments. And as the environment changes over time, for example, if you write your code for Python 3.5, and then eventually Python 3.9 is released, there could be something about version 3.9 that breaks your code, and if you just release your code as .py files, just source code in Python, you're not controlling for that. Another type of option is kind of in between the first two options I gave. So the first option I gave you was machine code, so binary executables. The second option was source code. JVM bytecode here is what Java builds. It's kind of in between those two. It's not machine code that's compiled to literally run the machine, but it is compiled code. It's not source code. It's code that the Java compiler produces to run on a virtual machine, which has instructions that are emulated by the different runtime environments. So JRE stands for Java Runtime Environment. Java runtime environments are available on a huge number of different OSs and architectures, basically a lot of different machines, from smartphones to different kinds of servers, Windows, Mac, whatever, Linux. And there's open source JREs and also proprietary ones from Oracle and IBM and others. Anyway, but those all understand this standardized JVM bytecode, which is sort of like compiled code that you'd have for like an x86 CPU, except it's not. It's designed to be translated and run on any kind of machine. So the purpose of this is to be able to allow developers to compile code and to compile it into a format that would be compatible with a single standard machine. So you have this single canonical machine, which is the Java virtual machine, that is emulated on any machine that you have. It's emulated by the Java runtime environment. And for performance reasons, the Java runtime environment actually will do some translation at runtime of like critical repeated code. It'll translate it into native code. So there's some just-in-time compiling from the JVM code to the actual, let's say, Intel x86 code if you're running on that kind of machine to make the performance good. But at the same time, it also is a generic. In general, it's a generic form of code that runs on any machine that has a Java runtime environment. So the slogan here for Java was that you write your code once and run it anywhere. So you write it once, you compile it once, and you run it anywhere, hopefully. In practice, it doesn't quite work like that. Unfortunately, the JREs don't all behave totally the same, but it almost fulfills this promise. And when you combine this JVM technology with like the Maven build system, Java becomes a very attractive platform for code that is very portable, that you can write once and run anywhere, and that's one of the reasons why I used it in this class. So one of the interesting things about this JVM is due to the success of Java and the JVM, I guess programming languages, people or really in industry more than in academia. But anyway, there are a lot of other languages now that have some nice new features or different features than Java, such as Scala, Kotlin. Those are languages you may have heard of that are pretty popular. Those languages actually compile to Java JVM code, and so even though if you program in Scala or Kotlin, it's a different language than Java, but it compiles to run on a Java virtual machine. So that the purpose of that was to reuse this infrastructure. These Java runtime environments were already built for the Java language. Now in these other languages, you also get that support of having this emulation layer that's available on lots of different platforms, except it supports lots of different. So the JVM actually has support for lots of different languages because there are compilers that will compile from all these different languages to JVM code. Okay, so the advantage of this JVM approach, Java Virtual Machine, is that you end up with compiling to, just like with binary executables, you end up with a small amount of code. We'll see this goes away in some later on. It's pretty simple. I mean, there's a lot of tooling that had to be built, but someone else built it for you. The performance is pretty good. It's not as good as native code, but almost. Maybe it might be like twice as slow or 3 times as slow, but it's almost there. It's much better performance than an interpreted language like Python or JavaScript or something. But the disadvantage here is that you're limited to one of these languages, like Java or Scala or Kotlin or one of these. And you have, once you start using outside environment, like if you start using command line tools or the file system through Java, it becomes less standardized and it's not really portable. So you would generally avoid doing those things. Okay. All right, so in talking about computing platforms, one of the key concepts in modern software development is virtual machines. And this is a relatively new development. Like these have become popular and essential over the past 10 years, I want to say, plus maybe a little more. But if you went back 10 or let's say 15 years, virtual machines were really not mainstream, and most software that was running would have been on servers, even like to run like websites and stuff. That would have been software that was installed on an OS. So you'd buy a machine, and then you'd like just install one OS on that machine. With virtual machines, by contrast, you have a single physical machine that runs that emulates several virtual machines through what's called a hypervisor. So a hypervisor or virtual machine monitor is a small piece of software that allows you to run multiple operating systems on one physical machine. And the purpose of doing this is to share resources and to allow you to have and to isolate different processes. So this is very similar to the concept to what an operating system does with processes. So an operating system, if you've taken the operating systems class, of course you know this, but assuming that you haven't, the main purpose of an operating system is to share resources. So you have one CPU, one set of memory, but you have many things you want to run. So you want to be able to run like a web browser and also a mail program and also listen to music. You want to do all those things at the same time on that one machine. So each has its own process. And there's a way that they have separate memory, and they kind of take turns using the CPU behind the scenes. The same thing kind of happens with a hypervisor and operating systems. So the operating systems that run, which are, I guess, the virtual machine operating systems, the virtual machines that run in a hypervisor are like those processes. So you can have many different virtual machines taking turns using pieces of the resources on a machine. It's not quite the same because usually you don't like swap the memory in and out. You don't move memory around. Usually you kind of like dedicate parts of the physical memory to different virtual machines, but the basic concept is the same. So there are different types of them, but the basic idea is you have a machine with many different operating systems. Like for example, you might have 3 different Linux operating systems running, and those are all configured. Those are totally isolated. The only way they can talk to each other is by communicating over the network. Even though they're on physically the same machine, they can't access the same files. They can't access the same memory. They don't even have the same. They might not even have the same users set up. They're totally separate virtual machines. There's a virtual network that the hypervisor manages that lets them communicate with each other, But the way these virtual machines on the same physical machine talk to each other is exactly the same as a virtual machine that talks to a machine across the world. It's all done over the network. Okay. So why do we use virtual machines? There's some inefficiency here actually, because we have this translation layer between the real CPU and memory that we have, and the virtual CPUs and memory that are allocated to the virtual machines. So the reason we do this, even though there's some complexity and inefficiency introduced, is to solve, like, I would say, two main problems. The first one is just being able to get really small. Well, okay, let's start with isolation. That's the first bullet point I have here. So let's say you want to run, let's say you bought one machine, right? And you want to share that between many services. For example, you want to have a web server and you want to have a mail server, right? Two servers you want to run. Technically, you can run those on one operating system, so there's no real necessity, there's no need to have a virtualization and to use virtual machines. You could have just one operating system. But the problem is, one problem with that approach is that those services can affect each other and cause problems for each other. So for example, if the web server has a memory leak or a security breach or the OS crashes, that will also affect the mail server. So like by memory leak, I just mean that the web server is just like uses lots of memory, too much memory, because there's a bug in the code. That will use up all the memory on the machine, and the mail server will be left with no memory to use, and so both of these servers will stop functioning. If we're using virtualization, what we would do is say, like, okay, half the memory is dedicated to the web server virtual machine, and half the memory is dedicated to the mail server virtual machine. Once the web server uses up its allocated memory, it's done. I mean, it stops working, but the mail server will still have its half the memory available. Okay, same thing. That same isolation principle goes for security issues. So if somehow the web server was hacked and someone gets access to it, they're not also going to get access to the mail server if they're isolated in two different virtual machines. Another benefit of this of virtualization is that you can migrate virtual machines and upgrade them. So if your machines are virtualized, or if your operating system is running on a virtual machine, then you can move from one machine to another very easily. If you have a cluster of machines that are virtualized, that are hosting virtual machines, so if you need to do maintenance on one, you need to turn one off, you could actually migrate the virtual machines to a different physical machine. And AWS does this to keep their systems running. So like I've had instances on AWS that have been running continuously for like 3 or 4 years. It's unlikely that they actually had the same machines like literally powered on for 3 or 4 years. It's very likely that they had to reboot them to do like operating system updates, or maybe to upgrade the firmware, things like that. It's possible they had them up the whole time, but like it's likely those things happen. And so in preparation for that kind of maintenance, they can migrate virtual machines off one physical machine to another. I mean, you need special support for the hypervisor, because while you're moving stuff, like things are going to be changing. You need to keep that synchronized, but this is possible. Also, by using virtualization, you can allocate small, cheap portions of machines to customers. So, for example, a machine that you would buy nowadays typically would have like 48 CPU cores and like more than 100 gigabytes of RAM. And it would cost a few $1,000s. So like Murphy has 24 CPU cores. It's a few years old. The new version of Murphy has like, I don't know, 96 CPU cores or some ridiculous number. But if I wanted to deploy a web server for my own website, like stevetarzier.com, I don't need that kind of power. I can't really buy a small machine. I mean, maybe I could buy like a Raspberry Pi or something, or like a really old laptop or something. But if I want to deploy this in the cloud, there's no one machine in the cloud that's small enough to fit my needs and cheap enough for me to pay like just like, let's say $10 a month or $5 a month for a little virtual machine. So instead, by taking these big machines that are available and allowing them to split their resources into small pieces, you can sell cheap web servers to customers, right? Because a lot of application code doesn't really require a lot of compute power. You can just run it on a small virtual machine. This also allows you to scale vertically. So like if my web page suddenly got popular, I could upgrade to a faster virtual machine. In other words, I could upgrade my instance to a bigger one, which would had a larger share of the CPU cores on its host machine and more memory without having to reinstall my OS or anything like that. It would just be like a reboot of the machine. Okay. That's a little bit about virtual machines. So EC2, you've used that before. It's Elastic Compute Cloud. Elastic means it can change in size. So the point of elastic computing is that as a company needs more machines, they just can very quickly buy them because they're billed by the hour, not the month. In the old days, so EC2 was started in 2006, so 14 years ago. At that time, it wasn't a totally new idea that you'd have a data center that was like outsourcing the management of servers to other companies. But at that time, the way that worked is that you would buy a machine from someone, from a cloud provider. It wasn't really called cloud computing, but you can think of it as the predecessor to cloud computing. You buy a machine from them, but you'd be paying for like by the month or something like that, because they would give you like a whole machine or something like that, and they didn't have the software to like automatically manage small virtual machines and give those out at a fine granularity. But EC2 did that. That was the service that really innovated that. So when you set up an EC2 instance, of course nowadays I should mention, of course, there are many competitors to EC2 from like Microsoft and Google. But Amazon really innovated the idea of letting customers very quickly set up virtual machines and charge like by the hour, not by the month. Anyway, so you can choose the size of the virtual machine, which is the number of CPU cores, the amount of RAM, and whether there's a GPU attached or dedicated to it, and the amount of network bandwidth. You can choose from various pre-set up operating systems, the type of storage, size of storage, the location, reservation periods just for billing purposes. If you reserve it for a year or 3 years, it's cheaper. And you give it your login credentials so that you can actually log into the thing. And they give you the IP address, and you get started. Okay. And you can create a virtual machine instance within a few minutes. I think you've done that in the homework. And you're billed by the hour. The hourly rate is somewhere between like 0.3 cents to $27 per hour. So that's quite a big difference. It could be somewhere between $2 a month or $19,000 a month. So this $19,000 machine obviously is a virtual machine that occupies an entire machine and a really fast machine with, I think, a lot of really fast GPUs and a lot of solid state storage. So this is like a really nice machine. Obviously, if you do the math, it's probably a machine that costs at least $100,000 or $200,000 to buy. Anyway, okay. So when using virtualization, I mean, one of the benefits of this is that you can outsource your hardware problems to a cloud provider like Amazon or Azure, but you still have many software operational concerns, which are generally called DevOps. So DevOps is a kind of portmanteau of developer and operations, and there are people at companies that do a combination of that manage software operations but without managing hardware, and that's generally called DevOps. Because you end up managing operations by writing code and managing configurations that are coded. And this includes things like figuring out, like basically setting up the platforms to be compatible for running your code, like configuring third-party software that needs to be installed. Also, it involves the process of actually deploying new versions of your application when developers update your application, but also monitoring what's happening. This is the operations part of it. So keeping track of looking for anomalies in CPU utilization, free memory, or disk space on your systems, or queues that are in your system, things like that. Or if queues are filling up, then that means that maybe the consumer of the queue needs to be made faster, and setting up security stuff. Yeah. Okay. So virtual machines are actually an app packaging and distribution option, because because of what I said earlier, that you can take a virtual machine and move it to a different instance, but also you can take an existing virtual machine and clone it and deploy it elsewhere. So you can do horizontal scaling by configuring one virtual machine and then cloning it and deploying it on lots of other instances of the same size virtual machine, right? So this is feasible. It's kind of an extreme option because it leads to like a really big application that you're deploying. It's like a whole virtual machine, which is a few gigabytes, at least 1 gigabyte, I would say. So what the virtual machine image is like basically a copy of a virtual hard disk that's big enough to install the operating system, all the libraries that are needed, all the software that has to be installed, and then the application itself that your company has developed. So this is going to be a lot bigger than the source code and the application itself because of all the operating system stuff that's installed along with it, which is probably not all of it even going to be used, right? So it's kind of bloated. On AWS, the virtual machine images are called AMIs, Amazon Machine Images, and there's some pre-configured ones. For example, if you want to deploy a MySQL virtual machine, you can, like, with a few clicks, you can deploy one that someone else has set up. But you can also create your own Amazon Machine Images from virtual machines that you have set up, and that's a way for you to deploy your application, clones of your application to lots of machines. Okay. So the advantage of this approach is that it gives you a very consistent environment because it's like literally a clone of this virtual machine. It's very controlled because you set up everything about the virtual machine. Because again, it's a clone of that virtual machine disk image. Because you're using virtual machines, your app is isolated from other apps. But the cons are that it's large in size. There's some performance overhead for running your app on top of a operating system that is running on top of a virtual machine monitor. A little bit, I guess that's not really a lot of performance overhead there. So maybe that, I'm not sure that's a big deal. But more importantly, if you're it takes a long time to boot up an operating system, like I don't know, 30 seconds or something like that at least. So that means that you can't. It takes if you want to do scaling really quickly and you're trying to do it with virtual machines, it's going to be pretty slow. Both because of the size it takes to like copy over your virtual machine image, that's pretty slow because it's a big thing. It's gigabytes in size, but also because the OS actually has to boot up freshly. So so it's kind of slow to deploy these virtual machines compared to some of the other options we'll see later that are a little bit more lightweight. Okay. So the next packaging option I'm talking about now are Docker containers, or you can think of containers in general. Docker is just the most popular kind of open source platform for creating containers. And this is like very similar to virtual machines, but it solves a lot of the problems of virtual machines I just mentioned. Okay. So just like a virtual machine, you get kind of like a consistent environment that includes the operating system being set up a certain way and other programs and libraries being installed. But we'll see how it's more efficient and smaller. Unlike a virtual machine, a container is intended to run just one process or app. And so it kind of runs on top of a virtual operating system that's pretty stripped down, typically. For virtual machines, we had a hypervisor that ran those virtual machines. The equivalent thing for containers is Docker. So Docker runs containers and hypervisors run virtual machines. And containers, you can think of containers in two different ways. So one is similar to a virtual machine as an image, like a disk image that runs the container. Another is a Docker file, which is like a sort of a blueprint for building that image in the first place. But with Docker, with Docker and with containers, we basically the clever thing about it is that you start off with some official base image, and there are a few of them. I'm going to actually open up real quick. There's a link in the slides to Docker Hub where all the official base images are listed, and these include like things like a standard Ubuntu setup to a setup that has Node installed or MySQL installed, or BusyBox, which is like a really small Linux deployment that might be suitable for an embedded system. Alpine is a really minimal Linux operating system, so this whole Linux installation is only 5 megabytes in size, compared to Ubuntu, which is like probably 100 megabytes or something. The stripped down Ubuntu is about like a few hundred megabytes, I think. Anyway, so these are pre-built images, kind of like the virtual machine images for these different operating system setups available for your container. But the clever thing about it is that your container uses that base image, and you can customize it using the Docker file. Here's an example of a Postgre Docker, the Docker file for the Postgre container. So there's a line up front that specifies that it's built off of a certain base image, which is Alpine version 3.11. This is a very small, the very small Linux image that I talked about. And then this Docker file specifies a bunch of commands for like setting up that operating system. So it's like you start off with a basic Linux installation, and then you like add a certain group, a certain user, you make a folder somewhere. These are all the things required to set up Postgre, which is a particular database. Okay. So you make some folders, blah, blah, blah. You download the software from a website, right? The details are not important, but like basically you extract it, and then APK add will, this is like install some libraries that you need to compile the software, and then you go in and make some tweaks to the source code and compile it. Okay, but these are steps. These are like a long series of steps that are needed to set up this particular database. But these can be repeated on anyone's machine, because wherever this Docker file is deployed, it's going to be starting off with this particular Alpine version 3.11 Docker file, which is a virtual machine that's going to be totally identical for everyone. Okay. So that little text file will actually create a whole container, specifies a container for Postgre entirely, because it builds off of a standardized Alpine container, and it provides instructions for setting it up, setting up everything else that it needs, including downloading software and whatnot. So that idea of specifying instructions for setting up an OS, it's very similar to operating system configuration management tools like Puppet, Chef, and Salt. And I think there are newer ones now that I haven't used. Okay. What else? Yeah. So containers are similar to virtual machines, but they run on Docker instead of running on a hypervisor. So at left, I have a container where you have different apps running on Docker on top of a host operating system. Virtual machines run on top of a hypervisor. Same basic idea, but the difference is that you have, with virtual machines, you have these different operating systems that are being run in parallel, that are needed for each of the virtual machines. I did say that Docker containers were based off of these virtual machine-like Linux installations, so that might be confusing, but let me show, we'll see later how that is made efficient and doesn't really duplicate as much as the virtual machines. Keep in mind that you can deploy Docker containers on top of a virtual machine. Usually everything we use are virtual machines anyway these days. So typically your container will be running in a virtual machine on a physical machine that's shared with other virtual machines. So these are not mutually exclusive, but they can be used together. Okay, but the secret of what makes Docker like more efficient than virtual machines is this layered file system that allows sharing of operating system components between different containers running on the same Docker platform. Okay, remember that containers are derived from a base image, which is a standard Linux installation. There are different options, but let's say we're developing two different images, or two different containers based on the same image. When you do this, you have an opportunity to share share the operating system components that are the same across the two containers. And this is done with the Docker layered file system, which is a copy on write file system. Okay, what does that mean? So at left, I have an illustration of two images that are both Elasticsearch containers. So Elasticsearch is a database essentially, and it's these Docker containers. There's a Docker container for Elasticsearch shown in this like green, olive green color here. This was set up to be based on an Ubuntu base image. So we start off with a base image of Ubuntu, and then we in the Docker file, it does some stuff to modify that image. Like, for example, it calls apt-get to install some dependencies. When it does that, instead of modifying the base image, it actually creates a layer on top of it. So everything in the original image is preserved identically, but there's some additional, that's why it's a copy on write. That's why it's similar to a copy on write file system. It's not totally copy on write. But we have this original image that is not modified at all. Then whatever changes we make to it are layered on top and kind of overwrite parts of the base image. The third step here was that the Elasticsearch application was installed, and so that made a further change to this image file system. And now we have an Elasticsearch image, which can be used by different containers. And we have two different containers that have different installations of Elasticsearch that build off of this same container in different ways. So one of them has some configuration files and custom environment variables that were added to the file system. And those create additional layers up here. But even though those layers were created here, another image running on the same machine, another container that's running Elasticsearch, still has access to this these shared layers below. And so it can use those. Both of these containers can share the lower layers that haven't changed. And that's the majority of data, and that's what makes it fast and more efficient than virtual machines. Because if this were a virtual machine, if we had two virtual machines running Elasticsearch, they would be each need full copies of the operating system, and there'd be no sharing between them. Okay, so Linux has good support. Docker's based on Linux and it runs only on Linux. There's a caveat to that, but because Linux has built-in support for isolating processes from each other, and that's what's used for the containers to be isolated from each other. So Docker takes that and builds on top of it this Docker file system for building these isolated processes, and the layered file system, and also this Docker Hub central image repository that you can use to build your own containers. So I already showed you one view of Docker Hub. Yeah. There are base images. There also are other published images that are not base images that... actually, what I was showing here were official images, not base images. Sorry. Base images are a subset of these. There are only 16 base images, sorry. So there's like Ubuntu, BusyBox, Alpine. These are all just basic Linux installations that don't have anything else installed. And then, yeah, then the longer list I was showing you of 162, these are actually official images that are approved by Docker, the Docker organization, but these build off of base images to provide things like databases and whatnot. All right. So Docker is tightly tied to Linux, but it also runs on Windows and Mac by running Linux in a virtual machine on those platforms, actually. All right. So the containers are isolated from each other, but unlike virtual machines, there's more. They kind of feel each other's effects because they share memory and CPU. So if we have two containers and one of them, let's say, has a memory leak, if we go back to that example, it would actually affect the other containers. So there's less isolation than with virtual machines, but the performance benefits are significant. Okay, so it's and this
it's a much kind of, I think, cleaner way of deploying applications that are on this generic computing substrate. Okay, so you can deploy containers in a couple of different ways. Amazon gives two basic options. So the first is to create a virtual machine cluster and deploy your containers to that. So basically decide ahead of time how many machines you're going to have. Like, for example, you might have 5 machines of the M4 extra large size. And you set those up and install a container orchestration system to manage that cluster, such as Kubernetes. Kubernetes is it's the standard open source container orchestration system. Amazon also has an Elastic Container Service, ECS, which is kind of like an alternative to Kubernetes that does the same thing, but it's less standardized. So using that creates a little bit of vendor lock-in. But anyway, if you use this approach, you have these virtual machines that you're managing yourself, and you can SSH into them for debugging. But you kind of need to provision the virtual machines first before you can use them. So that means you need to choose the size and number of virtual machines, which might mean that you have too many or you have too few. And if you have too many, you're wasting money. And if you have too few, then your system won't be running as fast as it can. Okay, so it requires more management. Then the alternative is to use managed infrastructure, and on AWS this is called Fargate. That's their managed container platform. And by managed here, when you say managed infrastructure, we mean managed by someone else, not self-managed. So it's like managed by Amazon. So in this case, you set up a container and then you deploy it to Fargate, and Fargate is just this nebulous like cloud platform that has infinite capacity, supposedly. Amazon will take your container and deploy it somewhere. We don't know exactly where. The cloud will find space for it. It could be on a virtual machine that's dedicated to you, or it could be a virtual machine that's shared with other tenants. We don't really know, although in practice I think that they're all dedicated virtual machines right now at least. All you do is specify the number of CPU cores and RAM size that you want for the container. Because it's not your own virtual machine, you can't SSH into it and do the same level of debugging that you can if you're using if you have your own dedicated cluster of machines for running containers. But the benefit is that you only pay when your code is running, and scaling is much more dynamic. So this Fargate system, like I said, has supposedly infinite capacity. You can just keep deploying to it, and once your containers stop running, you stop paying. Right, so you don't have to separately set up VMs and then pay for the VMs, then later deploy containers to it. All right, so that was a way of sort of abstracting away Fargate, which is just one way of deploying containers, as a way of abstracting away the platform. And we can take this idea even further with serverless functions. Okay, so with serverless functions, we write code and it would just run somehow, somewhere in the cloud. So it's the same idea as containers, except the packaging is different in order to make it to make kind of smaller things, smaller pieces of code that are deployed. So serverless functions are usually pretty small. And so it's a little bit of code that you write. So the idea here is to not have to worry about virtual machines or containers at all, and just think about code and have it run in the cloud somehow, and let Amazon or Microsoft or Google figure out where it's run. Okay. To make this magic happen, there are a lot of constraints placed on serverless functions. So by the purpose of the reason for this is that you want to use a generic infrastructure that should support lots of different tenants. Because of that, it has to be standardized. So if you want to use this shared infrastructure that has supposedly infinite capacity, you have to use that. That platform has to have a standardized environment that anyone can use. It can't be customized. You can't. So generally, this means you have to program in a particular language that works with the serverless function platform. Although, I mean, there's several available, like on AWS, you can use Python or Java or JavaScript and maybe one or two others to write serverless functions. But you have a limited choice of languages, and it has to be one of the certain versions that are available on the platform. On AWS, the serverless function system is called Lambda, and you can even write these. You can even deploy these by copying and pasting or writing code directly in a web browser with AWS. So you can. It makes deploying code to the cloud very simple, but it gives you a lot less control over the environment because you're using a very standardized environment. If there are any dependencies your app needs, they need to be bundled with your code. It's because you're only going to you're just going to install. You're going to provide one file essentially that's deployed, and that has to include everything that's needed to run that platform. With Python, you can install your pip dependencies in a subdirectory and then run your code with that. Your serverless functions are stateless, have to be stateless because once they run, they return and go away because they don't have their own dedicated platform. They can't like save to files or anything like that. I mean, probably you're developing your code in a stateless way anyway, so this isn't really a big constraint. But that's not a constraint that is required on virtual machines and containers because those have file systems that are available to them and because they're long running. Your serverless functions can't spawn command line processes. They just have to run entirely in their language. And they can only write to one folder in the file system, which is a temporary folder, which is not preserved after the code finishes running. Okay. So there's a lot of constraints, but the benefits here are that you can deploy code to the cloud without having to set up virtual machines in the cloud. And also, the granularity of scaling these things is much finer. So there's a lot less overhead to start up this code, a serverless function. So if your serverless function is a Python script or it's a Java jar file, then all you have to do is like the running that code is just is as simple as launching a Python interpreter or launching a Java runtime environment. So it's like starting a process on an already running OS, as opposed to deploying a container or virtual machine is kind of like booting up a new virtual machine, which can take like up to a minute or 30 seconds or so. So serverless functions can be very quickly spun up because they're just like programs essentially, little programs that are independent and can run on anywhere on this large shared infrastructure in the cloud that's standardized. Okay, so what you do is you deploy your code, you stage your code ready to run in the cloud, and then when your code needs to run for whatever reason, for example, if it's hooked up to an API or if it is triggered by something, like it could be hooked up to a queue in AWS or something. When your code has to run, then the cloud system will deploy your code somewhere to some virtual machine somewhere. You don't know where, you don't know how that happens. It just happens. And there's a short delay before starting it because it has to copy your function code to a new machine and start it up. If that's the first time it's running, if your code is running repeatedly, then there would be no delay for running it a second time or third time because the system would be smart enough to rerun it on the same machine where it was already installed. But that process happens pretty quickly. So that because the code can be very quickly deployed, the association between your code and a particular virtual machine is running is intended to be short term. So actually, for that reason, on AWS in particular, these serverless functions, lambdas, are limited to running for only 15 minutes or less, which is kind of annoying sometimes. But that's one limitation. Yeah, so when you're doing this, remember these serverless functions are designed to run on a generic platform, but that platform is specific to the cloud provider. So there's a lot of vendor lock-in here when you're using serverless functions, and that's one of the big disadvantages of using serverless functions. So on AWS, that would be Lambda. To use Lambda, you have to format your code in a certain way, or maybe use the libraries depending on what that they provide, depending on what language you're using. So it's difficult to migrate. If you're using a lot of serverless functions, it's difficult to migrate from one cloud platform to another. Although in practice, I think that's very unusual to do that. Usually when a company picks a cloud provider, they stick with them. Okay. So the big advantages here for serverless functions are the speed of scaling and the like really dynamic nature of scaling. So these are really good for infrequently executed code and really bursty workloads where you sometimes are doing nothing and sometimes you're doing a lot. Like you go from 0 to 1,000 parallel processes in seconds. You can do that. You can handle that with Lambdas. If you were trying to do that kind of like really bursty scaling with virtual machines or containers, there'd be a lot of startup time. And remember, with virtual machines, even you're billed by the hour. With serverless functions, you're billed by like the millisecond. Okay, so that's a very big difference in the granularity of the performance of starting it up, and also the granularity of billing, because of the very fast speed that the cloud provider can deploy your code, because your code is small and it runs on a generic infrastructure. Yeah. Okay, so we can compare the different computing platforms we've talked about here at a very high level. So virtual machines first, I talked about first, where you have a full operating system, which includes things like device drivers and like all the middleware and interpreters and stuff, libraries. Those are a good approach because they allow a lot of customization, but it's kind of leads to a very bloated application artifact, which is this whole virtual machine, which is several gigabytes big. If you wanted to scale horizontally by adding more virtual machines, you can do that by cloning the virtual machine image, but you have to boot up that virtual machine image to get it started, and that's slow. And virtual machines, if you're renting them from a cloud provider, are billed by the hour. So that gives you a limited granularity that you can scale things up and down. Okay, those are the disadvantages of virtual machines. When we move to containers, we get some of the same advantages, which is that we have this customized environment that we can set up exactly how we want it, just like with virtual machines. But it has less overhead because it has this clever layered file system design. And we can use Docker files to specify essentially the code for a container in just a little bit of text. So it's like you can specify a container with a Docker file, which is by writing some source code, and you can deploy that Docker file instead of with a virtual machine having to create a whole image of the virtual machine. Although technically, depending on the OS, you also can kind of do something similar with configuration management. So I'm not telling the whole story here, but they're similar. Containers are more lightweight. That's the basic thing. You also can use managed infrastructure with containers, more so than with virtual machines. So like I mentioned, AWS Fargate is a container management solution that's managed. So you can not have to like pre-buy your virtual machines, the right number of virtual machines, but rather just deploy containers as needed. And when the container stops running, you'll stop being billed for it. And you can deploy lots of containers at once, or just one or two, and you'll just be billed for the time the container is running. The container can quickly start and stop, not as quickly as a serverless function, but much more quickly than a virtual machine. So the extreme here on the right-hand side is serverless functions. These are a lot quicker to start up, and they can be billed by the millisecond instead of billed by the hour, because you're just deploying some like Python or JavaScript or Java code on a standard Python, JavaScript, or Java platform that's used by all of the tenants on that cloud. Disadvantages are that you have less access to set up an environment that has other like command line tools and stuff. You're limited to using certain languages, and also you're kind of locked into using your code and your system is very locked into that one cloud vendor's way of doing serverless functions. Right, because you're managing less yourself. Like virtual machines are standardized to just like the machine architecture like Intel x86. That's going to be available on any kind of hardware on any cloud. Containers also are standardized to run on like Docker and to be deployed with Kubernetes. That's open source stuff that's available everywhere. Serverless functions are much more customized to the particular cloud vendor, at least for now. They haven't been standardized yet. I want to point you to some tutorials for cloud architecture design. So when you're thinking about homework 6, designing some more complex architectures, you might see, you can look at these examples, and these examples on AWS. So these are, okay, so keep in mind, these architecture design examples were delivered by AWS to promote their services. And so the choices they make actually promote vendor lock-in and lock into AWS quite a bit. So they make a lot of use of serverless functions, which is okay, but it's not necessarily always the best choice. I didn't really talk about how Lambda serverless functions and containers were invoked. Containers you can think of them as running all the time like virtual machines. They don't have to be, but they can. So you can think of those as running services. Lambda functions are a little more, might be a little less clear right now, but know that Amazon has this thing called an API gateway, which lets you configure an API and specify the REST endpoints and connect each REST endpoint to a Lambda function that you've defined. So this is a way for you to use Lambdas to implement APIs and to implement backends, basically backend services. So these Lambdas, so the API gateway will be listening for requests all the time. It's kind of like a load balancer that has specified the API endpoints and has configured the Lambdas that handle each one of them. And if no one is making requests, then none of these Lambdas will be running, and you won't be paying for any virtual machines. Right? That's one of the benefits here. You will be paying for this load balancer, which is not free, but you won't be paying for any virtual machines. But then requests can come in at any rate, and as long as the load balancer can handle it, it can keep spinning up more Lambdas to handle the requests. Another thing you can do is use like these CloudWatch triggers for scheduled events that run Lambdas. Like if you have, basically you can replace the cron job we had in homework 4 to download from Common Crawl. You could do that with a Lambda instead. Yeah. Okay. So I talked about computing platforms today in this lecture. We saw a few basic options. Virtual machines are the most traditional way, where you have the full operating system, and the image of that, the disk of that virtual machine, the virtual machine disk image is like, can be cloned and deployed on many more virtual machines to horizontally scale, or to take an application that you developed locally and deploy it in the cloud. So you can build a virtual machine on your laptop, let's say, and then take that image and deploy it to the cloud. And you can deploy it many times to the cloud. Containers are a newer technology for deploying applications and setting up the environment for applications. They're similar to virtual machines. They're based on base images that have a basic Linux installation, but they have this clever way of doing layered changes to the file system, so that you can have customizations, different variations of a basic Linux environment, where a lot of the basic Linux stuff is shared across different containers that are running on the same machine. And it also has this Docker file for specifying images that's like a blueprint. It's like a little bit of source code that lets you in a very compact way, specify the container without having to have this big virtual machine image, disk image. And finally, we talked about serverless functions, which is code that's staged in the cloud, ready to run. And when it's needed, needs to be run, like for example, when a request comes in that needs to be handled by the Lambda, it's deployed to somewhere on demand by the platform. And it can be deployed more than once or just once. It can be deployed 1,000 times. The serverless functions allow you to scale very dynamically with really fine granularity, which is nice. And you can pay by the millisecond of time your code runs instead of paying by the hour. Disadvantage of serverless functions are that there's a cold start delay of a few seconds if your code hasn't run for a long time, if your serverless function has not run for a long time, and then a request comes in. Unlike a virtual machine that's sitting there and waiting, that you're paying for, Serverless function takes a few seconds to like copy that code to a virtual machine and get it started. That's the price you pay for not having to pay for a virtual machine that's idle. And the runtime is often limited to so 15 minutes right now is the limit for Lambdas on AWS. And also another con is that there's a lot of vendor lock-in with serverless functions. Okay, so I hope that made some sense despite the lateness and the hot weather in here. But take care and see you next time.